Good morning, Irvine. Happy morning to everybody. Another exciting day. Lucky to start out doing physics and even do more physics after we get started, don't we? Okay, let's see. If we have the capacity to store more information, the capacity, the ability to store charge, let's do a little more with that. I want to put in capacitors where we have more than one added in, capacitors in parallel and series. So we may have a capacitor, and if there's a circuit element where we want to add a second one or even more, putting a bunch of them parallel to each other, we can symbolically draw a picture of them drawn like this, and to try to figure out what is the equivalent capacitance. What is the equivalent capacitance of these guys if we were to think of replacing it with one capacitor equivalently? What value would that be? And once again, the reason people end up doing things like this is you may have a drawer full of capacitors and then need a particular value of capacitance for your circuit, and it's not one of the values that's in the drawers, but the drawers have enough of them that combinations of them might give you the value that you want. So if we look at this circuit over on the left, where I've drawn in the box areas a representation of a wire, an electrical conductor. If the capacitors are charged and sitting there with no current flowing, if there's no current flowing, the electric field inside the wire is zero. No current flowing, the electric field is zero. If the electric field is zero, no work is done going from the top of one capacitor along the wire over to the top of the other. If that's the case, then we know that both of the top elements are at the same voltage, the same potential. They're at an equipotential. So that means the charges on the top of C1 are at the same voltage level as the charges on the top of C2. Similarly, at the bottom, if there's no current flowing, electric field in the wires is zero, the voltage at the bottom of the two plates is identical. It's not the same as the voltage on the top of the plates, but it's the two bottom plates are the same. If the voltages are the same, we can bring the metal pieces holding the charge at the top plates together, and there will be no flow of charges. There's no electric field. There'll be no spark when the two plates are brought together. So we can bring these two plates together at the top with no change in anything other than just the location of the plates. Similarly with the bottom. And if we're thinking about capacitance being a geometric effect where it's some factor times the area divided by the separation of the plates, or some other geometric factor that's like this, what we've done by bringing the two plates together is taken the area of the first one, area of the second one, and made a larger equivalent plate that is just the area of both of them added together. So we can see that in this case then, it's going to go to epsilon A1 plus A2 divided by the separations. So what we see just on the physical basis alone is that the C equivalent is equal to the sum of the individual capacitances when we add them in parallel. The pattern, the mathematical pattern we've got here is the reverse of what the resistor pattern looked like. So you have to think it through a little bit, but on the physics basis, it guides you to what must be happening. In series, suppose we have some capacitors that are in series, something like this. And there's a voltage applied across the whole thing, right? So there's a voltage applied across there. Now let's take a look at these capacitors and see what happens. When that voltage is absent, So we have no charge on any of the plates, zero charge on any of the plates. And now we apply a voltage. So it's going to put, maybe we have a plus voltage, so it'll put a plus Q up here on the top plate. Because that plus Q is there, the bottom plate says, oh, negative charges are attracted to the positive. It's going to pull an equal and opposite charge on the other side so that the electric field in the wire below the bottom plate goes to zero in equilibrium. As a result, we have a plus Q and a minus Q. If we look at just the bottom plate from the top capacitor and the top plate from the middle capacitor, they are electrically isolated from the rest of the universe. If a minus Q was drawn up here to the top, then we must have left down below a plus Q. Similarly, as we go on down then, the same logic would give you this arrangement all the way through. Now, the voltage across each capacitor is not the same here, whereas in the parallel one, the voltage across both capacitors was the same. So we have a V1, a V2, and a V3. And V total is equal to the sum of those. And you can substitute in for the value of the voltage in terms of the charge, remembering that C is the charge per voltage. We get that for series capacitors, that they add in inverse. And it's a little tricky to do that. So whenever you do the inverse addition stuff for either resistors or capacitors, what you need to be careful to do is do the 1 over of the first one, plus 1 over of the second one, plus 1 over of the third one. In other words, take it down to very small steps, do each inverse, then add them, and then invert them again to get the equivalent at the end. So take those steps and don't rush through the math, because that's a very common error that people make early on in physics stuff with resistors or capacitors. They'll see, oh, those equations are so simple, go boom, 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 and then get the inversion problem not solved in the sequential order correctly and get the wrong answer. Okay. Now let's take a look again here at our capacitor resistor circuit that we have. So this is an RC circuit is what it's called. And what we've got is a capacitor that's charged up. And a resistor. The resistor is in fact this light bulb that we've got here, right? And so this is a 150 watt light bulb. So when it's lit up to its normal 150 watt brightness, that's pretty bright, right? And let's see, what did I charge it to? Let's find out. Let's go put it back there. Okay, so it's charged to, it's on the red guy. Oh, that's a pretty good charge. Okay, so let's see what happens here. This is where this charge gets stored. Storage of charge and dissipation of the energy over there on the resistor. So we have our capacitor and our resistor. Let's throw the switch and take our observation. How long does it take and what's the intensity as a function of time look like? Are we ready? Remember, physics is going to light up your life today. Here we go. How long did it take? 3 or 4 seconds, or how long was it at its brightest? Less time, right? So we see right away, we've made the observation, as we did last lecture, that the intensity, the power that we're emitting, the power, and this is the power dissipated in the resistor, right? So it's the power dissipated by the resistor. And it started out at some maximum value and it went down like this as a function of time. And what was that max level? How did that compare with the brightness you might expect to see on the bulb? If it was 150 watts, would it be about that bright? So it was somewhere near there, right? So it's on the order of 100 watts, 150 watts, yes?
What did you charge it to initially?
Initially charged to, now it's going to take a while to get back there. I think it was up to about 170 volts DC. Now it's less than that. It says it's 150 right now. Let's see what happens with this. Not quite as bright, but close. Okay, so if it was 150 volts on the peak going there, then the power went down like this. I'm going to describe this as an e to the minus t over tau. Tau is something you commonly use for a lot of different meanings. And it might mean the period of a wave, for example, inverse of the frequency. But here it's just a time, but it's a characteristic time. If the time little t up here is 0, what's the value of this exponential? It's e to the 0, and the value of e to the 0 is 1, uno, right? Okay, now, if the value of the little t for time is equal to tau, this is e to the minus what?
1.
Tau over tau is 1, so it's e to the minus 1. And what's e to the minus 1?
1 over e.
1 over e, and that's, so remembering e to the minus 1, that's 1 over 2.718, right? That's 1 over e, right? Okay, so 2.7 for e is a little bit less than 3, isn't it? So 1 over 2.7 is a little bit away from 1/3, but not a lot. So if it's going to 1/3 of its value, 1 over e, an e-folding is what we call this. If it's gone an e-folding value, 1/3 approximately is about here. That's tau. As you watched with your eyes, you saw the visible light start out maximally, and then you saw it dim away. We'll try another shot just to let you see it again. And so the tau time was about how long?
1 second.
What you could see was it's somewhere around a second, right? Maybe it's 3 seconds, maybe it's 1 second. And your eye is seeing the visible light portion, but as the voltage drops a bit and maybe the temperature of the filament changes, and a lot of variables that don't make it just a ballpark kind of estimate, but still something we can work with. Okay, let's take a look. Ready? Here we go. Okay, maybe it's on the order of 1 second, 2 seconds, 3 seconds, somewhere around there. Should we try this other bulb? So if we change the value of the resistance, what will happen? Let's take a look. Let's see if we can predict while the thing is charging up. Let's do a prediction. Let's apply those Kirchhoff's rules that we talked about last time. So if we want to apply let's look at the voltage going around. Now, of course, you see up there at the top of that drawing, the switch is open. So what we're doing visually with this switch is closing the switch, literally rotating it on a hinge and bringing it down there. Okay, so let's take a look at with the switch closed. Switch closed. switch closed at t equals 0, and then let time run. Let the clock run. Okay, what's the voltage look like at t equals 0? We've got a voltage on the capacitor. So that we have, let's see, we know that capacitance is the ability to store charge. So the voltage on the capacitor is equal to the charge on it divided by C. And then this is going to be a function of time, isn't it? The voltage on the resistor is going to be I times R. Oh, let's see. That's equal to R dq dt. And that is the same Q we're talking about as on the capacitor, because the capacitor pushed the charges. Now, in fact, let's think about that just a little bit. Didn't I say that when the power company pushes the charges, they kind of wiggle around here, but we never really see a charge that came from the power company? So similarly, the capacitor is on a wire that's a distance away from the resistor. The charges that pass through the resistor, the dq dt, the current through the resistor, is not identically the same charges. But when you put a little bit of water in one end of a hose, it pushes the same amount of water out the other end. And so we're getting that process going on. Every charge that leaves the capacitor pushes one downstream through the resistor, and they are the same. The dq dt is what's leaving the capacitor. Okay, here we go on the longer one, right? This one took longer. Are we ready? You are getting sleepy. Whoa, look at that guy. How long does that take? And if I wasn't talking, you'd have got your numbers a little better, huh? Don't be distracted by things, right? Never talk on a cell phone while driving. You can't measure things well if you're distracted. Period. Hands-free or handheld is the same, or very nearly the same. Okay, so you got your time for that? Or did I distract you?
15 seconds. What was the original voltage?
I don't know. Gesundheit squared. Okay, so let's see now. Our voltage around that, we apply the Kirchhoff rule, the energy rule. Let's go around our loop then. So we have the voltage over the capacitor and the voltage drop along the resistor add up to any battery supplied voltages that are there. But in this circuit, we had the battery hooked up and then took it out of the circuit, and it's just this guy up above. There's no voltage supply there, so this is 0, right? So what have we got? Oh, let's get this guy. So I've got Q over C plus dq dt times R equals 0. Yes?
The equals 0 because the eventually light comes out. Is that what the reason?
No, the equals 0 is very simple. We're just doing energy accounting as we go around the loop. Start somewhere, look at the voltage drop. Oh, there's the capacitor. Go around, nothing, nothing. Over here to the resistor. Oh, voltage drop across the resistor. Back around to the bottom of the capacitor, and we're done. There were no sources of EMF, no batteries or power supplies. That would make the 0 something different. We'd put a script E there if there was a battery, for example. That, I don't know what that's called, but that's so neat, right? The old cursive writing style. Okay? All right, so let's take a look here. I got a Q and a dq dt, and I got an R, so let's dq dt is equal to, let's move stuff over, minus Q over RC, dq over Q is minus dt over RC. A differential equation. Not too hard. Can we integrate? We're very good at integrating, right? I'll tell you what, I'll do the one on the right. So we do an integral dq over q equals minus integral dt over rc. So the RC, R and C are constants. Remember, C it doesn't change in time, neither does R. So I have integral dq over q is minus 1 over RC integral dt. This one is not so tough, huh? And so this is just minus t over RC. If we wanted to, it's going to go from t equals 0 to t equal whatever t final is, and that's going to be t final minus 0, right? So it's going to be minus t final over RC. That should be a little f. Okay. How about this guy? What is dq over q? Whoa. dq over q. That's the 1 over. That's the one integral that does a bizarre thing. Log of q. Evaluated from q initial to q final. Okay? Log. So that's telling me that the log of this is equal to minus tf over rc. Do you guys like dealing with logs? No, we're not in the lumber business. Let's just stay away from that as much as we can. Let's go and get rid of the log by doing an exponential on both sides. Can we do that? Yep. Why not? Now we did it, didn't we? That's so loud. You can do that, right? We have chalk. We can do it. So if we do that, e to the log is what? 1. Yeah, they cancel each other, don't they? So we're just left with the q final minus q initial. The change in q goes as. Let's see, logs, the differences are divided, aren't they? So this is q initial e to the minus t over rc, t final. Let me just make sure you saw that as a little aside. Remember, when you're doing your integrals, that log of q from q initial to q final is log q final minus log q initial, and that's equal to the log of q final over q initial. So I did that in my head. It's not so interesting as the math. Now, I'm sure if you were taking a math class, the math person would be going, this is really interesting, the other stuff's not so interesting. It's the physics. So you have to go with whatever perspective is going to get you the best path through for learning all of it. Okay, so what this is saying is that the charge diminishes as the charge flows out of the capacitor. The charge diminishes at an exponentially decreasing rate. Let's take a look at that. So that says Q as a function of t versus t starts out and goes like this. And this is our initial. And then here's at some time wherever we want t final to be on that time scale. And it is diminishing as a 1 over r so tau equal to RC is called the RC time constant. Let's see if it makes sense. If we have very little resistance, very small resistance, then when the current is allowed to start flowing, there's nothing to oppose the flow very much. There's a very small opposition to the flow. If there's a very small opposition to the flow, the charge can leave the capacitor rapidly. If R is very small here, then RC is small. It means that it doesn't take very long for t to get big enough to be the same as tau. So if R is small, the RC time constant is small, and it discharges the capacitor rapidly. Let's imagine if the capacitor is made smaller, if its capacitance is smaller. Then the amount of charge it holds isn't going to be so much, but it can also get rid of that charge faster for a given voltage. If the capacitance was huge, lots and lots of charge is stored, then it's going to take a long time to get rid of the charge. If the resistor is really big, it takes a long time to push past a very tough resistance. If you go to one of these food places that sells like shakes and malts, and you buy it and it has a straw that has a very tiny diameter and it's pretty cold for the shake, a lot of resistance, right? Takes a long time to empty that shake capacitor, right? So it makes sense. So the voices of nature are telling us what's going on here. Makes sense. All right. Okay, let's do some more fun stuff. Volunteer. A volunteer. Have you helped, sir? You have. Have you helped? Would you like to now? Okay, let's see about what we can do here. All right, hi there, I'm Roger McWilliams. Hi, how are you today? Good. All right, let's see now. I think this thing is set up backwards, so we're going to reverse the direction of this thing by doing this, and then we'll find out if I'm right. What do you see?
I see something that sort of looks like a drill, and the glass basically.
Okay, so there's a glass with some metal inside. There's something that looks like a drill. Doesn't that look old school?
Yeah.
That is very old school. In fact, the drill element, the handheld part of it, is made of something called bakelite. B-A-K-E-L-I-T-E. That was possibly the first plastic. The first moldable plastic. I'm not sure if it was first, but it's from around that time. So that's one of the earliest moments where we got better life through chemistry. The chemists starting to have some important contributions. Now, I think they probably made some earlier, but I'm amazed by bakelite. I mean, plastics and stuff are amazing inventions. Okay, so anyway, hooray for chemists. And now let's try turning this thing on and see what happens. Ready? Not much, huh? Whoa. Wait a minute. Let's, do you want to touch that?
No.
No. Why don't you want to touch that?
It has a charge, most likely, because of the drill.
You saw, yes, you saw. Let's take you can see it pretty well from there, right? Okay, so the bottom of this drill-like thing is a rod that comes to a point. Not a really sharp point, right? But there's a point there. Yeah, I'm not hurting myself doing that. You can do that. Okay, so there's a point that's got a radius. The radius at the point is about 2 millimeters. And we're applying a voltage. Did you hear the hum? Humana, humana. And so this is taking power from a 110 volt line, running it through a transformer here, which we don't know about yet, but makes high voltages. There's a knob here on the end which can be turned to vary the voltage. And it puts that voltage there on the end. And you saw from the Van de Graaff generator, when voltage got high enough for a given radius of curvature, you could have breakdown of the air. Do you see breakdown of the air?
Yeah, whenever there's light, it's limited.
You see it?
Yeah.
Okay. And what color is that breakdown?
Green.
In the air.
In the air?
What do you see for the spark right there?
It's like almost silverish. Like
So-
it's like whitish. This,
Silverish with a little purple?
yeah.
You see the purple?
Yeah.
Okay. Now, this device is also a medical device. Back when chemists figured this out and physicists knew how to make sparks, the biology community took this device, this very kind of device, and put little extra things on the end like combs and things, and then use it to get rid of head lice. So if you had a lice infection, you could go to the doctor and they would zap your head with this thing. If I was lice, I don't think I would like that. But if I was a person, I don't think I would like it either. So I think you can still buy these things for that purpose.
What's it called?
I don't know. It's the head lice zapper. I don't know what it's called in the medical world, but it comes in little cases, and doesn't that look gruesome?
Yeah.
Yeah, maybe we could do electroshock therapy with it too. Okay, so let's take a look at now the green. Let's focus on the green. Okay, so when we got the gap small enough that the voltage caused an arc, it jumps from the end of the tip over to this tube, and then it makes I forgot your name.
Tamar.
Tamar
Yeah.
says it makes green stuff. Let's take a look at the green. Where's the green? Can you guys see that okay? Can you see it up there? Middle, can see it? Can you see it over there? Okay. What's it making a green what? You see a green streak, okay? So there's a green streak. There's a piece of metal in there.
Yeah.
Okay, she agrees. And the metal has a phosphor coating, phosphorescence. Okay? And since we're doing energy and doing it very efficiently, it must be green. So we have a green phosphor inside, and what do you see down there at the end of the metal?
At the end, there's like, it's like half circular or like almost like a parabola, and it has like a line like bisecting it. It's like this.
It's called a slit.
Oh, slit.
Okay, so we have, yeah, she's got the right description. The metal piece goes along down to the end and then is bent forward towards you guys, which blocks the flow of anything coming from the end. And there's a small slit, a horizontally made slit. So if something comes from this end that gets excited by that voltage, if something comes from there, then it can travel along, and if it goes through the slit, it can continue to travel. If it doesn't go through the slit, you're not going to get to see it, right? Because it's get blocked. It's like, you see my eyes? You see them now, right? And if, well, oh, that didn't work. Okay, anyway. Then if something is traveling along and hits the phosphor and has enough energy to excite the phosphor, then you see it. Do we see it? Okay, tomorrow. Now the excitement builds. This is what?
Magnet.
Possibly a magnet. See if it sticks to metal. Does it stick?
Yeah.
Okay, now take the magnet and move it up and down here without breaking the glass. Oh! Whoa! My sakes. What's happening to the green? Okay. Oh, okay. Oh, that's a good one. What color is the end of the stick here?
Black.
Red.
Oh.
Red. Okay. She is correct about what she said, by the way. I'm just wanting to emphasize the red end of the stick. Push it down, and which way did the right go like that? Which way does it go?
Goes down.
Goes down. Okay, now flip the stick over. Blue. Which way does it go? Oh! Check that out. Okay, now let's try actually moving it right behind. Oh, look at that. Okay, so what we are seeing here, now see, she's going to remember this because she did it. All right? You want to grab that end? You'll remember that too if you do that. I'm not sure that's a good idea. Do you want me to try it? It might blow out the electronics, I don't know. Okay, so anyway, I'm charged up enough as it is. Okay, let's say thank you very much, Tamara. Appreciate it. Okay. Okay, now let's get some notes down about what she has done, right? What did she do? Something, that spark gap caused some electrons to be emitted inside that tube. And those electrons went along as an electron beam. So we made an electron beam. The ones that went through the slit, some of them got scraped off along the side, hitting the phosphor as they're going along the edge of the electron beam. And the metal phosphor piece is not actually straight. It's got a little curvature to it, so as it scrapes off the beam, it can get a little further down. So what you're seeing there inside that tube is electrons have been accelerated and travel along, and then where they hit the phosphor, they have enough energy in the beam to light up the phosphor. It only takes a few volts in energy to do that. Yes?
Was it the positive side that made it go up or the negative side?
Oh, the positive side that made it go up or the negative side? And this is a magnet. So you might ask yourself in the sense of positive or negative. And magnets, instead of using the term positive or negative, we typically, for historical reasons, refer to it as a north or south pole. So this is, you know what, Tamara? I think when I look at this, it's closer to black than dark blue, isn't it? You may have been better described than me. Anyway, I'm going to go with navy. Then we're covered. Okay. Here's the navy guy brought. What's it do? Down. And here's the red one. Oh. There's the red one. And here's the navy one. So the navy one pushes them down and the red one brings them up. For this way, right? And it doesn't really matter. What we saw that does matter is that the electrons were deflected. They didn't touch the magnet, but they were deflected. And they were deflected in what direction? Sideways, right? Very bizarre. They're going along and there's a magnetic field and they got directed sideways. So what we've just seen now is that moving electrons can experience forces from magnetic fields, and that those forces are sideways. That's a strange thing to have to cope with mathematically, and we're going to do that.
I have a question.
Yes?
When you say sideways, you just mean perpendicular to the...
Perpendicular to the velocity of the electron.
Right.
Sideways means perpendicular to v, the vector velocity. Okay? Good question. Okay, so we're now approaching magnetism. And what we saw there is, well, you know there can be a magnetic attraction, right? There also, we just saw, can be a magnetic repulsion. So it can bring one direction or the other direction. So there can be attractive and repulsive forces. And we saw that with electricity by itself also. Opposite charges attracted, similar charges repelled. So our first observation then is that magnetic forces are experienced by moving charges. So if you knew what the speed of the electron was, or the energy of the electron here, and you saw the path that it took, you could talk about what the actual forces on the electron are. Now, F equals dp dt, right? The change in momentum. And you saw that the electron beam could be made to go 90 degrees in only a couple centimeters there. So there's enough dp dt on the individual electrons to get them going 90-degree different angle in only a couple of centimeters of horizontal travel. And you go, wow, that's impressive. It takes quite a bit of force to turn me in a couple centimeters 90 degrees. So remember, the electrons have a mass that's 9.1 10 to the minus 31 kilograms. They're just little iter-bitters. So they can be readily moved, but we could estimate what the forces were. So what we saw was, if there was a charge moving with some velocity v, and if there was a magnetic field, this thing suddenly went zoom like this and could continue. So the magnetic force was perpendicular to the velocity vector. And the magnetic force depended on having the charge present. The magnetic force depended on having the charge present, right? Do you feel? No. You don't, right? You don't. Is there anything there? Do you feel anything? No, no, no. Okay, so if things are neutral, you're not going to feel a lot of force from the magnetic field. Is it possible for people to feel magnetic fields? What do you think?
Yeah. If it's really strong, maybe.
If it's really strong, have you ever heard of any human being feeling magnetic fields? I have never heard of any human being feeling magnetic fields. I've heard of people saying, oh, I feel the aura.
What about if you have like two magnets and you can feel the resistance of it?
Well, you can feel the forces between the two magnets, but you're not feeling the magnetic field yourself in that sense. So I work with magnetic fields every once in a while that get to be pretty large, and the only time I have ever felt directly something from a magnetic force field on my body is when I was standing in I guess it was about a 12 kilogauss field, which was made by an electromagnet. We're going to do that in just a second. And somebody in another room leaned against a switch and turned the magnet off very abruptly. And so the magnetic field collapsed from 12 kilogauss down to 0 in less than a second. And I got dizzy. And so I went outside and I saw the magnet had dropped to 0. Called him up on the intercom, said, hey, is the motor generator system working right? The guy said, oh, it's all working fine. I said, well, my field just collapsed. And they went, oh. And then off the record, they told me some guy leaned against the switch by accident. So anyway, apparently if the dB dt, if the magnetic field changes rapidly enough in time, there can be an induced electric field, we'll find, which did cause me to get a little bit dizzy. So my neurons got a little bit deranged by having that happen. I consider that an asset. Okay, so we don't normally feel magnetic fields or recognize them for human beings, but there are some animals that use magnetism on the planet for navigational purposes, and that seems pretty cool to me. Okay, so what we're finding is that F is QE, as we are used to it from the electric field, plus a new force, Q V cross B. That's the one that's new to us now. And what the heck is that? We've been dealing with dot products for doing work, but there's a cross in there. That one's a cross product. So don't think of it as an X. Think of it as a cross product. B. The magnitude of B, this is the magnetic field, is equal to the magnitude of the force per unit charge per meter, and has the angular dependence in it from the cross product. That's the definition of the magnetic field. Remember, for electric field, compare the electric field the magnitude of the electric field was defined as the magnitude of the force per unit charge. The definition of the magnetic field is more complicated. It is a force per unit charge, but it's got a V and a directional element in it as well. So if the magnetic field is parallel to the direction of motion, let's look at examples. V parallel to B. Then F from the magnetic field has Q, magnitude of V, magnitude of B, sine of the angle between V and B. This is V and B, then theta is 0. What's the sign of 0? 0. So this says that if they're parallel, then the magnetic force is 0. If V is perpendicular to B, then sine theta is sine of pi over 2. And what is that? 1. And F magnetic equals Q V B in terms of magnitude. If the angle is somewhere in between 0 and 90, then the force is in between this QVB and 0. And the direction of the force, this is the really neat thing here, but also the really hard thing. Let's imagine, everybody do this. We're going to have the velocity is this way. So stick your head, aim for the eyeball of the person in the seat to the right. Okay? To the right. And now I want you to curl your fingers towards the chalkboard. So it's like they start out with your middle finger in the direction of the velocity, curl it towards the chalkboard, and we'll call that the direction of the magnetic field. Are you giving me a thumbs up? Right? A thumbs up. So that's the direction of the force. We go V, curl our fingers into the direction of B, and our right hand thumb gives us the direction of the force. It's upward. That's cool. A magnetic field pointing towards the board would take a particle moving to your right and push it upward. That's bizarre, isn't it? Nature does some neat things. Okay? So you use the right-hand rule. It's V crossed into B, and your thumb points in the direction of the resultant force. Don't use your left hand. Now let's imagine just a little further on there. It's Q V cross B. What happens if Q is negative? Now it's V cross B is up times a minus, so that the actual direction of the force is anti-parallel to your thumb, right? It's downward then. Yeah, like the ancient Romans. No, right? Okay, if it's a negative, then it's down, right? Okay, so remember, you do your V cross B and get the direction of V cross B, then multiply by plus or minus for the Q to get the final direction of the vector. So if we had electrons going along and they went up in this diagram for the demonstration, and then if we put protons going along same velocity, they would be oppositely directed. So that means that if we had a beam of electrons and protons, then they would get separated like this, wouldn't they? And if the charges get separated, what happens? Now we build up electric field. It's like a capacitor, right? And there will be an electric field pointing this way, right? And that's going to do something with the charges also. So life gets very complicated very quickly when you start moving these charges around. And I get very excited about that because that's plasma physics, the fourth state of matter when things are well ionized. Which tends to mean it's really hot, like the sun. Okay, so let's see, we've built some. Oh, let's look. What do we have here? What is that? Okay, demonstration. See, Harry, you've already helped. Have you helped? You've helped. No, I have to go. Yes, sir, have you helped? Come on up. Give us a hand. We'll get you. Have you helped already or not? Okay, we'll get you next. How's that? Oh, it'll be a joyous moment. Okay, and you are?
I'm Charles.
Charles?
Nice to meet you.
Yeah, hi, nice to meet you. I got to get just a little more chalk on my hand. It doesn't work for you, but I'm going to get him a second time. I'm sure he couldn't hear what I said. Come on over here, Charles. Okay, Charles, what do you see?
Some kind of pole.
A pole, plexiglass pole, right? With a little tape here to keep these guys from going off, right? And then just move them around a little. What do you see?
Ooh, magnets.
They're magnets. And as you push them closer together, what happens to the force?
It gets stronger.
It gets stronger. Can you push them together?
No.
No, give it some welly. Can you?
I don't think they're actually touching.
You can't do it, can you? Okay, so what we're discovering here, let's see. And how much force did you apply?
A lot.
A lot. So we got the qualitative start going, right? A lot. Now let's see if we can quantify what was a lot. What would be the maximum downward push that he could give?
Body weight.
His body, yes, you're thinking on your feet. So 750 newtons, right? And you didn't do that, did you? There was still weight on your feet. So why don't you see it? Do you think you had half your... I don't want this thing poking through your neck or something either, right? So don't be too exuberant. What do you think? Quarter of your weight?
About, yeah.
So 200 newtons was not enough to make these magnets touch. And you observed that as you got them closer together, the force got stronger. Okay, so now, if these are magnets, and we just said that moving charges feel forces from magnets, well, here's a magnet, and here's a magnet. They're feeling forces on each other, right? So there's a possibility then that at the microscopic level, in these magnets, there are charges that are moving. We didn't make them in the light bulb thing over here, in the cathode ray tube. We didn't make them over there, but they're naturally residing in the metal, and maybe they're making lots of little tiny racetrack spins down at a microscopic level. And then we see that the magnetic field from the other magnet makes a force that tries to repel, move them away from there. So we have in our mind then the possibility of something in addition. There are microscopic moving charges making the force, and maybe microscopic moving charges make magnetic fields. Now we have an additional complication. Moving charges make magnetic fields. And we're going to come back to that. Was that exciting?
Very.
You're easily excited, Charles. Okay, that's a good thing in life. Shall we? Let's see about doing stuff here. Okay? Well, that's not so good. Let's try that. Okay. Grab this stuff, some of it. I don't know which. Let's do lights. Let's try 50% for now. Close. It's here to begin. Okay, so take a look at that. Take a look at the others. Play with the magnet a little bit. you're going to do different things with them. We'll go dock cam. Okay, that's terrific. Now, don't we need a screen? Okay, so let's do it over here with, I'm going to try this guy to start. I want you to notice this. Go around, do that kind of stuff. See what you see there for a second while the screen's coming down. And you'll become the expert here, right? See that? Isn't that easy to do? Okay. Can you make the, the little bird shadow stuff? Do you know how to do that with the lights? Can you do that kind of stuff? You know, oh, Zot, there you go. Do that one so they can see it. That was a sideways anteater. Go ahead and give them an anteater symbol. It'll show up there. There we go. That's a great anteater, huh? Okay, so now what the heck? This screen thing just doesn't quite recognize what we want, does it? Shall we go? Let's try more lights. Oops. Document camera light on. How's that? Is that better? Oh, yeah. Okay. All right. Now, Charles, what do you see? Let's put this here. You like it like that? No, that's bad. Is that better? Is that better? How's that? Okay. Charles has a magnet. He's going to bring it in from the side. What happens? And okay, so bring it where it just is at one place and then bring it to a halt. So what do you see for the direction? Now let's bring it on to here a bit, just a little bit on, and keep it flat. Okay, keep going, and then rotate it in the middle. What happens to these little particles of things? What are we seeing them do?
Rotating.
At the ends, let's look at the blue end. What happens to the direction of those little kind of like nail pieces that are there? They move towards it. They're pointing towards it, aren't they? They're kind of lining up on it, as if, like that, they lined up, right? Okay, that excitement is about over. Now let's do another one. Oh, we've invented a free energy source. Okay, here you go. Do something. Ah, it gets stronger as you get closer, doesn't it? Yeah, huh? Yeah. Okay, so what we're seeing here is that the magnetic field depends on the distance, doesn't it? The magnetic force depends on the distance. And in fact, let's bring it to a halt so they can see. We have the two colors. Are we going to call them black and red? Because I think we'll go with tomorrow's description. Okay? So black and red are two ends of the magnet. And when we had two ends of electric charges, remember that was a plus charge and a minus charge, and that was then an electric dipole, right? So what we're seeing here is a magnetic dipole. And how did the electric field go from a dipole in terms of distance? Remember, point charge was 1 over r squared. When we've got two charges nearly canceling each other, it must fall off faster than that, so it falls off as 1 over r cubed. Magnetic dipole, we're going to look for magnetic fields falling off as 1 over r cubed. And it does happen. Okay. Oh, and look, I can do it too. Okay, let's try a different one. Why don't you bring that guy over? Just put this guy down on top of that. Now this one, oh, this one, it is so cool. Look at the little tiny arrows. Each one of those little pivot compass things is a little tiny arrow with a tail and with a fletching and a tip. Fletching. You ever heard of that? Fletcher? Have you ever heard of somebody named Fletcher? What does that mean? The fletching is the the stuff on the back of an arrow that helps it go straight. So a fletcher would be somebody who put the little feathers on arrows. You believe that?
Yeah.
I think it'd be worth looking into. Okay. So my wife's last name before we got married, her last name was Carter. What do you think a carter meant? Somebody who moved carts, right? And now whenever she's mad at me, her last name is Carter, and when she's not mad at me, it's McWilliams. Okay, so what we have here is seeing the arrows come out on the red side and going in on the blue side, right? So we do have a dipole field shape here, don't we? Look at the way they line up. I bet Charles could even draw that on the board, right? It's a little easier to see it up there, actually, than down here, isn't it? Okay. What's that next one over there? Let's put that one in. What is that?
Some kind of liquid.
Liquid? Here. Why don't you just put that guy down in the middle? Well, that's about as exciting as killing ants with a magnifying glass. Let's put it down here. You know, I'm gonna...
It's moving.
It's moving, yes. It's alive. It's alive. Not all of physics is exciting. What we can do, though, is put on your fast-forward helmets. Right? What's happening here? Not much. Okay, Charles, I think that this is about the dullest demo. No, we have a demo that didn't work at all. We probably did. I tell you what, let's add some excitement for Charles, because this is about the level of dullness that we can't take any more of. Okay, so lights, room control, lights on. Great, screen, come on. Screen, up. Charles, stick around. And we need another person to help with the demos. So come on down and give us a hand. Literally a hand, okay? Hi, I'm Roger McWilliams. Okay, I didn't catch it, so spell it for me.
Roopkamal.
Roopkamal.
Yeah,
You should have said that.
that's what he said.
Oh, thank you very much. That's helpful. I can picture it with the letters, but I can't always get it from the sounds. Thank you, Roopkamal. Okay, so let's see now. Oh, Roopkamal, this is Charles. Okay, do you guys trust each other?
Yeah. Okay.
Bad move.
I'll trust no one.
That's a guy. Do you trust him? Let's just be straight.
Oh, yeah.
No, you don't, okay? Don't, right? This is a gal. Don't trust him. Okay, now, okay, so what do we got here? Charles, you do this part. You're over there, right? Okay, so now what we've got is a couple of disks. You remember when we had the Magdeburg hemispheres and we put a vacuum between them and then you couldn't pull them apart, right? Okay, so now there's no vacuum here. What we've got is two pieces of metal that are near each other with a stop so that it doesn't go wham and somebody gets hurt, right? And then what we can do is you guys can pull it apart, right? Yeah. Okay, let's do this. You hold with both hands. So yours is clearly still, and you just keep rigid, and Charles can do that, right? Okay, and now you prove you can do that. Okay, so it could be pulled apart easily enough. Now, all we have here is a wire, a battery, and a coil of wire wound inside. And now I'm going to hook this one up, bring them together. Okay, you ready? Pull it apart. You are not worthy. He has not proved his ability to do strong work to you.
Oh, no.
Are we ready? Watch out, watch out. Now, can you pull?
No.
Oh.
Oh.
Okay, let's take a look here and see what we have. Let me see if I can take it apart without breaking it. But if we break it at this point, it worked already, so we're good. Right? Okay, what do you see?
Is the coil?
The coil. Okay, on your right, we see a coil. Boy meets coil. Okay, a coil, and it's wound in there, and there's some fabric as insulation, right? Okay, and over here, just a
Metal.
piece of steel. But is it will it hold a magnet? Evidently, yes. Right? Okay, but it's not magnetic on its own. Go see if it sticks to that. No, nada, niente. Okay, do you want to try that again?
Try what? Pulling it?
Yeah.
Okay.
Oh, let's leave it with that off. Why not? Equal and opposite, right? He cannot pull stronger than Roof Kamal. Right? Maybe you are stronger, but as she is opposing, you can't, unless you drag her with you. Right? Okay, so that's enough. So now can you, oh, here you go. So all it was a little flashlight battery, right? Okay? That was more exciting, wasn't it? Okay? Thank you, madam. That was very gracious of you. Thank you, Charles. Oh, so the insulation on the coil looks like it's a sort of cloth. I want you to imagine back more than 100 years. Let's imagine back to the early 1800s when Michael Faraday was doing things, Joseph Henry was doing things. Joseph Henry, yes. Joseph Henry was one of the guys that helped invent the telegraph. And he did this work before he became the founder of the Smithsonian Institute in Washington, D.C. He was up at a little school in New Jersey called Princeton, and I went there for graduate school. And there's a really neat thing in the physics department. They have closets where they keep old equipment from stuff from a long time ago. And you can go and find these old equipment that people used from 100 years ago to do stuff. Anyway, Joseph Henry was married, and apparently happily so, as me. And he did his physics lab stuff, maybe a little closer than my house is to my lab. And he figured out how to make the telegraph, which required making some windings where the wire is close together like that. And it was reported that to insulate the wire, well, first you must have wire. That's not so easy to get when wire isn't routinely made. Then you need to have insulated wire. And what he is reported to have done was have taken one of his wife's silk stockings and unthreaded it, and then patiently wound the thread of the stocking around the wire to make the insulation, as we see in there, although not done with silk stockings, I imagine. And then that wire he ran from his laboratory back to his house, and then when lunch was ready, his wife would telegraph him, make the telegraph work to tell him to come home for lunch. Wow. My wife doesn't do that. She says, you want lunch? Find it. And she makes lunch for me most of the time. Okay, so magnetic forces are made by moving charges, making magnetic fields, and are experienced by moving charges. Screen control, stop, video mute. Are experienced by moving charges. And if we have, let's go to here for this. if we have a moving charge like that, current, electric current, is dq dt, and it's the amount of charge passing through a defined area that we pick. So if I have a wire with lots of charges all moving at the same velocity, then I have a current flowing. And if there's a current flow, how long is this wire? It's some length, right? So it's a meter, it's some meters long. Let's say that it's this length. And if there's a magnetic field, it's pointing up. Let's see if we can figure this out. We want to do V cross B. So we take our fingers and we get them pointing in the direction of V. Okay, I've got them pointing over there in the direction of V, but I got to curl them in the direction of the magnetic field. Oh, that works. Okay, so you go like that. Now you curl it, and Harry, it's a thumb in the eye, isn't it?
Yes.
Okay, so that's the direction of the force for this one on that drawing, right? Okay, so that's what you do. You figure it out. You got to contort your arm until you get the right stuff. We got V cross B straight out at you guys. And we have that for each of the charges that are moving at this velocity. So now what we get is the magnetic force macroscopically goes as I L times B. That has the velocity in it, the total charge that's in it, and the magnetic field. But, does that equation have the direction? No, this is just a scalar equation. So we have to think now a little bit more. F mag is going to be I times L cross B, if you want to do it that way. And I've now given a length, some direction, didn't I? We have a choice. We can either give the current a direction or the length of the wire. They are identical in their path, so it doesn't matter which one. So let's use the length and say that the length direction, the direction of L, is defined to be the direction of that velocity of the charged particles on the wire. So now we got a direction for L. So we have microscopic QV cross B, and we have macroscopic IL cross B. Either way. Can we go kind of intermediary, in between, where it's not quite so macroscopic but not entirely microscopic? Yes. Let's now bend the wire. So the wire goes along something like this. That looks kind of like a nematode, doesn't it? Okay. So here's the wire, and we got the current going all along it like this. But what's the direction of L? Now it's not so clear, is it? And so we might look at one little chunk of it right here. And let's call that a length dl. So it's a microscopic length, but it's carrying the macroscopic current through that part of the wire. So here's what we would say is the contribution to the force on the wire would be I dl cross B. And we're kind of in between macroscopic and microscopic when we do that. magnetic fields, how big are they? Here is the Earth. And so we've got magnetic fields that reach out like this. And the magnetic field at the surface of the Earth, say, if we're right here, this is La La Land, right? Los Angeles. Here we are. Anyway, the magnetic field at the surface of the Earth is about half a Gauss. Sometimes when fields are about that size, we use a unit that's called a Gauss. But the magnetic field in MKS units is Tesla. And 1 Tesla equals 10 to the 4th Gauss. So the magnetic field that you are feeling right now from the Earth, although you don't get much reaction to it, is about 10 to the minus 4 Tesla. Yes?
What's the subscript on
B, MKS, as in meters, kilograms, seconds, right? The MKS units on the subscript there, right? But when we're talking about stuff at the surface of the Earth, it's pretty common to talk about Gauss. And then sometimes way out in space things where people are talking about things that are really tiny magnetic fields, they talk about different units like Galileos. And so there are all kinds of units, just like with charge, right? What's the unit we use for charge for MKS? Coulombs, right? But 200 years ago, we could have used Franklin's. And actually, for a lot of the theory side, when I do calculations, I use something called electrostatic units, ESUs. Use whatever's convenient. Okay, so half a Gauss is not very big. And we don't feel it too much, but the birds and the bees, some of them do. If you go to see medical things, right? Let's see, what's that called these days? MRI, right? The sort of more physically correct description is nuclear magnetic resonance. But biology people and medical people know that the general public is afraid of the word nuclear, which apparently, in my mind, is not so new and not so clear, apparently, to some people. So anyway, nuclear magnetic imaging, MRI stuff, uses what kind of magnetic fields? Around a Tesla, sometimes a little more than that, right? Sometimes less than that. You can get higher resolution, the higher the field you can go to, but it takes a lot of skill and energy to make higher magnetic fields. It's hard to do. I had the very good fortune one time of visiting Bell Lab folks in the mid-1970s when I was in graduate school and got to meet Purcell, who is the Nobel Prize guy who did MRI, the nuclear magnetic resonance imaging stuff. That was a great moment in life to be near a great person like that. I like that quite a lot. Okay, so what else do we need for magnetic forces? I think that may be it for today then. All right, remember on Monday we have another quiz, right? The excitement continues.